There's one detail the market has almost completely ignored while everyone's been arguing about Tesla's robotaxi, Optimus, or AI ambitions. About 35 miles outside Houston, in Texas, Tesla is quietly building what could become the largest solar factory in human history. Not the biggest in America, not the biggest in the West, the biggest in the world. And if what Elon Musk just confirmed is true, it could eventually reach 100 gigawatts of annual production capacity. A number so massive that even a lot of energy experts think it sounds completely absurd. But here's the part that makes this story way more interesting. Tesla isn't just talking anymore. The company has actually started building it. For years, whenever people brought up Tesla Solar, the most common reaction was basically disappointment. After Tesla acquired Solar City in 2016, Elon Musk promised to turn the company into the center of the clean energy revolution. New York even spent nearly $1 billion in subsidies to build Tesla a massive factory in Buffalo, hoping it would become the biggest solar manufacturing hub in the Western Hemisphere. But things almost immediately fell apart after that. Panasonic took over production, then pulled out in 2020. The Buffalo factory gradually became more focused on making supercharger components and processing autopilot data than actually producing solar products. Tesla Solar declined so badly that the company almost stopped mentioning it in earnings reports altogether. Then suddenly, toward the end of 2025, things started to change. Tesla quietly began producing a new solar panel called the TSP-420 at its Buffalo facility. By early 2026, the product officially launched commercially in the US. Most people assumed it was just a small attempt to revive a business segment that had already failed. But it turned out that was only the beginning. At the World Economic Forum in Davos in January 2026, Elon Musk unexpectedly announced that Tesla and SpaceX would independently build enough solar manufacturing capacity in the US to reach 100 gigawatts per year, covering the entire supply chain from raw materials all the way to finished panels. At the time, most of the market treated it like another classic Elon Musk statement: too huge, too crazy, and basically impossible. But then CNBC revealed that Tesla was negotiating to purchase around $2.9 billion worth of solar manufacturing equipment from China to ship to Texas. And now, we finally know exactly where all of this is happening. Brookshire, Texas, an area near Houston where Tesla has reportedly leased more than 1.65 million square feet of industrial space, with plans to expand by several 100,000 more square feet in the near future. What makes this even more interesting is that this is also where Tesla is building its roughly $200 million Megapack megafactory. That's not a coincidence. Tesla is trying to create a fully integrated energy campus where Megapack battery systems and solar panels are manufactured side by side. It sounds simple, but it's actually a huge deal. Because in Tesla's long-term vision, solar and battery storage are basically inseparable. A utility-scale solar farm needs Megapacks to store electricity. A house with rooftop solar needs a Powerwall to operate efficiently. Tesla doesn't just want to sell solar panels. The company wants to control the entire energy ecosystem. And that's exactly why this factory could reshape the entire global solar industry. Because this isn't just a normal solar panel assembly line. Based on the information that's been confirmed so far, Tesla is building a fully integrated manufacturing operation in Brookshire. That means everything happens in one place: silicon ingot pulling, wafer cutting, photovoltaic cell production, and final panel assembly. This kind of vertical integration is extremely rare in today's solar industry because most companies still rely on multi-layered supply chains across Asia. In other words, Tesla is trying to do with solar what it already did with electric vehicles: control as much of the production process as possible. And that's exactly why Houston matters so much. The city has one of the largest ports in the United States, which is basically essential if Tesla plans to import billions of dollars worth of industrial equipment from China. That's something Austin simply doesn't have. Houston also offers massive industrial logistics infrastructure, a strong skilled labor pool, and the ability to scale giant factories much faster than most other places in America. But the thing that really shocked the market isn't the factory's location, it's the scale. Right now, Tesla's Buffalo factory only has around 300 megawatts of annual production capacity. The new target is 100 gigawatts. That's more than 300 times larger. And Tesla supposedly wants to pull it off in less than 3 years. To put that into perspective, look at First Solar, currently the largest domestic solar manufacturer in the US. By 2027, the company is expected to reach roughly 17.7 gigawatts of capacity. Tesla is aiming for nearly 6 times that amount. Not globally, just from a single complex in Texas. And this is where the story starts sounding almost unbelievable. The total amount of solar capacity installed across the entire United States in 2023 was only around 32 gigawatts. In other words, Tesla wants a single factory to produce more than 3 times the amount of solar panels that the entire US deployed in 1 year. That's why a lot of people are calling this plan completely insane. And honestly, the skepticism is understandable. Elon Musk has made more than a few overly ambitious promises in the past. Solar roof was once promoted as the future of construction, then almost disappeared from the conversation. The 4680 battery program took years longer than expected to reach real commercial scale. Even the Tesla Semi ended up arriving far behind schedule. But there's one major difference this time. Brookshire isn't a subsidy-driven project like Buffalo was. No state government is writing Tesla a giant check in exchange for jobs. There's no political build first, figure it out later model here. Tesla is using its own money. Based on current estimates, the manufacturing equipment alone could cost close to $3 billion, plus hundreds of millions more for clean room facilities and construction infrastructure. The total investment could easily exceed $4 billion before the factory reaches full scale. And here's the key point. Even if Tesla fails to hit the 100 gigawatt target, the company could still completely reshape the solar industry. Because even if Tesla only reaches 20 or 30 gigawatts per year, it would instantly become one of the largest solar manufacturers in the United States. If it reaches 50 gigawatts, Tesla would effectively surpass most of the current domestic industry by an entirely different order of magnitude. And if that happens, the solar industry could be entering a completely new era. But while all the attention is focused on Tesla's 100 gigawatt solar factory in Texas, the company just did something in California that felt emotionally like the complete opposite. At the Fremont factory, Tesla held a special ceremony marking the end of an era the moment the final Tesla Model S and Tesla Model X rolled off Tesla's traditional production line. What made the event so significant wasn't simply that a vehicle was being retired. It's that the modern auto industry as we know it probably wouldn't exist today without the Model S. As Elon Musk, Franz von Holzhausen, Lars Moravi, and longtime Tesla engineers stood beside the final cars, the atmosphere didn't feel like a product launch. It felt more like a reflection on history. Because before the Model S, most of the world genuinely thought electric cars were a joke. Back then, EVs were seen as glorified golf carts with weird designs, slow performance, and disappointing range. The idea of a luxury electric sedan that could outperform gasoline cars was considered almost impossible. But Tesla completely changed that narrative. The Model S wasn't just a good EV. It was the car that terrified the entire automotive industry. Tesla emphasized during the ceremony that the Tesla Model S was the first EV ever to achieve more than 400 miles of range. It was also the first mass-produced car capable of accelerating from 0 to 60 miles per hour in under 2 seconds, a family sedan with hypercar-level acceleration. And for a long time, almost no car in the world, including gasoline vehicles, could beat it in short-distance drag races. But what truly shocked traditional automakers wasn't just the speed. It was the way Tesla broke almost every old rule in the auto industry. Back in 2012, putting a massive 17-inch touchscreen in the center of a car was considered a crazy idea. Most automakers were still building cockpits packed with physical buttons that looked more like airplane controls. But Tesla viewed the car as a technology device rather than a traditional mechanical machine. That's why the Model S pioneered the concept of OTA software updates. The car was no longer fixed the moment it left the factory. It could continuously improve over time. Today that sounds completely normal. But in 2012 it was practically science fiction to the global auto industry. And that's exactly what made Tesla so dangerous. The Model S didn't just compete with electric motors. It dragged the entire auto industry into the era of the software-defined vehicle before the rest of the industry even realized what was happening. Even the very first Founder Series cars from 2012 are still on the road today. Elon Musk and Lars Moravi even revealed that they personally drove their own Founder Series cars to the ceremony. It's a tiny detail, but it says a lot. A more than 10-year-old electric car is still good enough for the people who created it to keep using every day. Tesla also revealed something incredibly interesting that a lot of people don't know, even though today's Tesla Model S and Tesla Model X still look fairly similar on the outside to the original 2012 and 2015 versions. They actually share only about 3% of their parts with the original cars. The total number of components has also been reduced by more than 40% compared to the first generation. This is Tesla engineering in its purest form: constant simplification, constant cost reduction, and relentlessly eliminating anything unnecessary. That same philosophy is now showing up again in the Cybercab and even in Tesla's new solar factory in Texas. Tesla has become increasingly obsessed with reducing part counts, minimizing manufacturing friction, and removing unnecessary complexity everywhere possible. And the Model S was where that mindset first became truly visible. But if you look deeper, the biggest success of the Model S wasn't its sales numbers or technical specs. It was the fact that this car completely changed the world's perception of electric vehicles. Before Tesla, most of the auto industry believed EVs could only exist as economy cars. After Tesla, EVs started becoming the best cars. That's a massive difference. Tesla didn't sell compromise. They sold superiority. Faster acceleration, air suspension, a quieter cabin, more advanced technology, lower operating costs. For the first time, car buyers started wanting EVs not because of the environment, but because they were simply better than gasoline cars. The ceremony at Fremont factory also brought back memories of one of the craziest bets in Tesla history: lithium-ion batteries. Back when the Tesla Model S was still in development, almost the entire global supply of lithium-ion batteries was being used for phones and laptops. Tesla needed battery volumes that were many times larger than what the market had ever supplied for automobiles. At the time, a lot of experts believed mass-market EV production was impossible simply because there wouldn't be enough batteries. Tesla went all in anyway. And that gamble eventually changed the entire global energy industry. What's interesting is that we're now seeing the exact same pattern repeating itself with solar. A lot of people today are also saying the 100 gigawatt target is impossible, that the supply chain is too complicated, that Tesla is exaggerating. But those are almost exactly the same things people were saying about the Model S more than a decade ago. And that's why the most emotional part of the ceremony wasn't the numbers. It was the moment Elon Musk made it very clear that Tesla's future will no longer revolve around driving. Tesla believes full self-driving technology will eventually make human driving something rare. And that's why the company is shifting resources away from traditional flagship vehicles and toward robotaxi and Optimus. In other words, Tesla has just closed the opening chapter of the EV revolution and is now moving into the next phase. The Cybercab has already entered pilot production, with mass production expected to begin as early as next week. Tesla says the vehicle achieves energy efficiency of around 165 watt-hours per mile, a level of efficiency that has almost never existed before in a full-size vehicle. And that matters because Tesla is no longer optimizing cars for drivers. The company is now optimizing for AI fleets, for the lowest possible operating costs, for maximum utilization, and for the largest-scale automated manufacturing system possible. And then there's Optimus. Tesla confirmed that the final section of the old Tesla Model S and Tesla Model X production line at Fremont factory will now be converted to support manufacturing for the Optimus humanoid robot. The company wants Fremont to become one of the largest automation hubs in the world, with ambitions to eventually produce up to 1 million robots per year. Just think about that for a second. The same place that once produced the electric sedan that saved Tesla from bankruptcy will now become a factory for mass-producing humanoid robots. It's almost the perfect symbol of how Tesla operates. This is a company that never stays in one industry for very long. The moment the rest of the world started catching up in EVs, Tesla shifted toward AI, robotics, and large-scale energy infrastructure. Elon Musk is playing an all-in game in Europe. The $250 million investment to expand battery production capacity from 8 gigawatt-hour to 18 gigawatt-hour at Gigafactory Berlin-Brandenburg is not just a number. It is a declaration of war aimed at gaining absolute control over the supply chain. By vertically integrating everything, producing everything from battery cells to finished vehicles at the same location starting in 2027, Tesla wants to eliminate its dependence on Panasonic and LG Energy Solution. The objective is very clear: cut logistics costs, capture more profit, and respond to market changes at lightning speed. At the same time, Musk accompanying President Donald Trump to China was a pragmatic political move to protect Tesla's position in the world's largest EV market and pave the way for full self-driving amid pressure from BYD and NIO. However, this aggressive expansion strategy appears to be inversely proportional to the actual performance of the 4680 battery. The promises made during Battery Day 2020 about a revolutionary next-generation battery have been challenged by reality after 5 years of deployment. Technical data shows that the 4,680 cells produced in Austin only achieved 244 watt-hours per kilogram, roughly 13% lower than the 269 watt-hours per kilogram achieved by Panasonic's 2,170 cells. On the European version of the Tesla Model Y, replacing LG batteries with 4,680 cells, reduced total capacity to 79 kilowatt-hours, directly causing WLTP range to fall sharply from 661 kilometers to 609 kilometers. The biggest failure lies in fast charging performance and weight reduction. Although Tesla promoted the tabless design as a thermal breakthrough, the real-world charging curve of the 4,680 battery has proven less stable and slower than previous generations. Even the new structural battery pack only makes the vehicle approximately 9 kilograms lighter compared to versions using 2,170 cells, a negligible improvement considering the drop in overall performance. Tesla is now facing a contradiction, investing billions of dollars to mass-produce a battery technology considered the future, while real-world specifications appear to be moving backward compared to products supplied by external partners. The contradiction between Tesla's multi-billion-dollar investment and the declining real-world performance of the 4,680 battery at Gigafactory Berlin raises a major question. Why does Tesla continue betting on a technology that appears to be moving backward? The answer does not lie in short-term driving range figures. It lies in a hidden revolution inside the manufacturing process itself: dry electrode technology. This is the key that allows Tesla to transform battery production from a bulky and expensive chemical process into a high-precision mechanical manufacturing system similar to semiconductor production. In exchange for complete vertical integration, Tesla appears willing to accept early shortcomings in energy density in order to eliminate giant drying ovens, replacing them with acoustic systems and ultra-precise rolling techniques capable of optimizing cost and scale at unprecedented level. How has Tesla revolutionized battery manufacturing through dry electrode technology? The most important part of the 4,680 story is actually not the battery format visible to consumers. It is Tesla's attempt to completely reinvent the entire electrode manufacturing process through dry electrode technology, one of the boldest moves in the lithium-ion battery industry in decades. Traditional battery factories today still primarily rely on wet coating processes. In these systems, active materials are mixed with chemical solvents to create slurry-like substances similar to paint. The slurry is then coated onto copper or aluminum foil before being sent through massive industrial drying ovens to evaporate the solvents. These drying ovens can stretch for hundreds of meters, consume enormous amounts of energy, and occupy most of the floor space inside a battery production line. According to many industry analyses, the drying stage alone can consume more than 30% of the total energy used in an entire battery factory. Tesla wants to eliminate this entire step. In a dry electrode system, battery materials remain in powder form. Instead of creating liquid slurries, the powders are directly compressed into films and pressed onto metal foil without requiring solvents or giant drying ovens. If successfully scaled, this technology could allow Tesla to reduce factory footprint, cut manufacturing energy consumption, reduce machinery requirements, accelerate production speed, and lower battery cost per kilowatt-hour. This is why Elon Musk once described dry electrode processing as a manufacturing revolution rather than merely a chemistry improvement. However, turning dry powder into stable electrodes is extraordinarily difficult. Liquid slurries naturally spread evenly like paint, while dry powders behave more like flour or sand. They easily clump together, crack, fail to adhere properly, and become extremely difficult to manufacture consistently at industrial scale and high speed. One of the earliest challenges involved the binder material PTFE, commonly known under the brand name Teflon. PTFE can form microscopic fiber networks that hold active materials together. But PTFE also creates serious problems. If too much is used, energy density decreases because PTFE itself does not store electricity. Even worse, PTFE can electrochemically degrade during battery operation. According to technical documents related to dry electrode manufacturing, PTFE can cause irreversible capacity losses of up to approximately 127 mAh per gram, an enormous energy loss for modern lithium-ion batteries. Tesla initially experimented with combining PTFE with other polymers, such as PVDF and polyethylene, to reduce the losses to roughly 30 to 50 mAh per gram. Tesla also discovered that binder particle size plays an extremely important role. The company uses a high-performance Hosokawa 100 AFG jet milling system operating at approximately 120 pounds per square inch, with classifier wheels rotating at around 8,000 revolutions per minute to grind binder particles down to roughly 10 micrometers, similar in size to a human red blood cell. Matching binder particle size with conductive carbon particles nearly doubled the tensile strength of the electrode films, increasing it from approximately 0.936 newtons to around 1.74 newtons. This allowed the electrode sheets to survive industrial roller systems without tearing or producing debris. But Tesla did not stop there. Eventually, the company decided to almost completely eliminate Teflon. Instead, Tesla shifted toward elastic polymers such as polyethylene combined with acoustic mixing systems. Unlike traditional mechanical mixers that use aggressive blades capable of crushing active materials, Tesla's system uses sound waves to vibrate and disperse powders evenly. Tesla operates the mixing system at approximately 60% intensity for around 5 minutes to achieve optimal material distribution without damaging fragile anode or cathode particles. As a result, the company achieved active material ratios approaching 99%, meaning nearly the entire electrode volume is used for energy storage rather than inactive supporting materials. This becomes critically important because if particles fracture during processing, fresh chemical surfaces become exposed and react with lithium during the very first charging cycle. That permanently reduces battery capacity before the vehicle even reaches customers. To solve this issue, Tesla developed a multi-stage mixing architecture. One processing stream is used to activate the polymer binding network, while another stream protects active material particles from mechanical damage. Only afterward are the materials gently recombined. This process is now considered one of Tesla's most important manufacturing secrets because even if competitors understand the chemistry behind dry electrodes, reproducing Tesla's precise automated production process at large scale remains extremely difficult. The greatest challenge lies in dry cathodes. Cathode materials are far more abrasive, harder, and much more difficult to compress into stable films than anodes. Sharp particles can damage rollers, crack electrodes, and create uneven coatings. This became one of the biggest bottlenecks, delaying large-scale 4680 production for years. Tesla responded by redesigning the cathode particle structure itself. The company added aluminum and boron before applying a two-stage heat treatment process at approximately 800 degrees Celsius, followed by around 700 degrees Celsius to transform sharp crystal structures into more spherical particles. These particles reduce mechanical friction with machinery and improve movement through high-speed production lines. Tesla also had to develop entirely new rolling systems. The rollers not only compress the material but rotate at slightly different speeds to create gentle internal tension within the electrode film. This allows continuous processing without tearing. The rollers are heated to approximately 185 degrees Celsius and rotate extremely slowly, sometimes at only around 1 revolution per minute. This process warms the polymer just enough to stabilize the structure without damaging active materials. The required precision is extraordinary. Some roller systems apply pressures reaching approximately 450 kilonewtons, equivalent to multiple heavy trucks pressing directly onto the electrode layer. The gap between rollers must remain within approximately 1 to 30 micrometers. Even microscopic vibrations can destroy electrode uniformity and shorten battery lifespan. Tesla reportedly uses specialized tapered bearings, hydraulic balancing systems, real-time sensors, and terahertz inspection systems capable of scanning electrodes directly during production. Some inspection pulses last only around 1 to 5 picoseconds, enabling detection of microscopic defects measuring approximately 0.05 to 0.5 millimeters directly on high-speed production lines. In many ways, Tesla's 4680 production lines now resemble semiconductor factories more than traditional automotive plants. The success of this technology depends not only on electrochemistry, but also on Tesla's ability to maintain ultra-high precision continuously at massive scale. Why is the 4680 battery considered the foundation for robotaxi, AI, and Optimus in the future? The reason Tesla continues investing billions of dollars into 4680 technology is because the company does not view it as merely a battery for cars. Tesla sees the 4680 as the large-scale energy foundation for its entire future ecosystem, including robotaxis, the humanoid robot Tesla Optimus, AI data centers, and large-scale modular energy storage systems. Personal vehicles spend most of their time parked, but robotaxis will operate almost continuously, potentially driving hundreds of kilometers every day and fast charging repeatedly. This level of operation causes conventional lithium-ion batteries to degrade extremely quickly. To solve this problem, Tesla is researching a hybrid structure between lithium-ion batteries and activated carbon supercapacitors. The idea is to create a battery that can both store large amounts of energy like a conventional battery and withstand ultra-high power charge and discharge cycles like a supercapacitor. This is especially critical for robotaxis because autonomous fleets require maximum uptime to generate optimal revenue. If the battery degrades too quickly or charging takes too long, the entire robotaxi economic model could collapse. At the same time, Tesla is also preparing for the next generation of silicon-rich anodes. Silicon has the theoretical ability to store roughly 10 times more lithium than graphite. This could dramatically increase battery capacity without increasing battery size. However, silicon has a major disadvantage: it expands extremely aggressively during charging, sometimes by as much as 300%. This expansion causes materials to crack, break electrical connections, and accelerate battery degradation. Tesla has developed several solutions to control this phenomenon. One approach involves creating ultra-small spherical particles through spray processing methods, where silicon is surrounded by flexible carbon nanotube networks. When the silicon expands, the nanotube network can expand with it without breaking electrical conductivity. Another strategy uses polyacrylonitrile coatings treated at temperatures of approximately 200 to 400 degrees Celsius to create ladder-like conductive polymer structures. Tesla also uses roughened copper foil with an Rs surface roughness greater than approximately 1.5 micrometers to improve silicon adhesion. In addition, Tesla increases the internal porosity inside the electrodes by around 50 to 70% to create expansion space for silicon without destroying the overall battery structure. If Tesla successfully scales 4,680 production, the impact of this technology could extend far beyond electric vehicles. The 4,680 battery could become the large-scale foundational platform for robotaxis, humanoid robots, grid-scale energy storage, and even the global AI infrastructure that Elon Musk is attempting to build through Tesla.